Okay, previously we talked about the linear system of equation as well as matrix and its property. Now we will discuss a little bit more about a concept that run along something called determinants. Okay, calculating determinant is very important, especially as you see earlier, in which by using determinants we can calculate the value of inverse of a matrix, where inverse of a matrix can be applied or used for uh, various calculations related to solving linear equation system. Okay, here we will talk about three topics. First is how to calculate determinants, basically by using cofactor expansions, and then by using another approach such as row reduction approach, and then finally we can use the property of determinants of a linear systems to find a solution for a linear system, which is called Cramer's rule. Okay, as mentioned earlier, this chapter we will discuss about a notion called determinants. Okay, determinants, and uh, when we know this, the value of a determinants of a linear systems, we can use those to find an inverse or of an invertible matrix. So we will try to find a specific formula in which how we can calculate those determinants. Earlier we have been introduced about if you calculating a determinants for matrix for a square matrix 2 by 2. Um, in order to we know that it is invertible if and only if the value of uh, the diagonals a multiplied by d minus the other diagonals minus b multiplied by c is not equal to 0. And these expressions is also known also as determinants of those particular matrix A. Recall that in order to get this, we can write it like this one. Determinants can be write it like this one, like it's equal to this one, or you can also write it as this one, where you have two bar long bar uh, besides the entry of the matrix to represent that, okay, I want to calculate the determinant of this particular matrix. And in order to calculate the inverse, it represented by this notion, you can calculate by 1 per those determinant of matrix multiplied by the value of those is being interchanged. Now, instead of using different formula for each uh, um, matrix, we will try to find a formula that applicable to all square matrix of all order for calculating its determinants. So, in order to do that, we will introduce you to a concept of minors as well as cofactors of a matrix. So, take example of the matrix that we have earlier, matrix A, where each entry were denoted as A11, A12, A21, A22. Okay, now in order to calculate the determinant of A, or using these symbols, you have A11, okay, this one A, B, C, D, yeah, AD, AD minus BC, yeah, A11 multiplied by A22 minus A12 multiplied by A21, okay. Now, if you define the determinant of a 1 by 1 matrix, it's only contain of 1 and 3, so the determinant of 1 by 1 matrix is the value of those matrix itself, okay. And As mentioned earlier, in order to make a general concept of how to calculate this determinant, we will use new terms called minor of an entry. Okay, now it's denoted by Mij. So each what is a minor of an entry Aij? So it will be related with the each row and column. Okay, I will be row, J will be column. Each minor of entry of Aij denoted by Mij is defined by the determinant of the submatrix that remain after I row and J column are deleted. For example, if you have A here, A11, A12, A21, A22. What is the minor of 1, 1? Minor of matrix 1, 1. Okay, this is 1, 1. Okay, so you delete the row matrix related to matrix 1 and then the column 1. So the determinant of a matrix of a minor 1, 1, minor matrix 1, 1 is this one, A22. Now try it again. What about the minor of A21? So you need to delete the second row and the first column. So you have A12. Okay. Okay. That's about the minor of an entry. Okay. Now what about another term called cofactor? Okay. It is represented by this one, Cij. Okay. It is the number of minus 1 to the power of I plus j multiplied the value of those minor. Okay, so let's say this one, you have Mij. So if you are asked what is the cofactor of C11, so you have minus 1 to the power of 1 plus 1, so minus 1 square multiplied by the Mij, the one that you have earlier. Okay, so this one Cij will be equals to Mij. Okay, so next. Okay, now let's use those definitions that we have earlier about minor and cofactors. You have this uh, matrix. Okay, now you want to find the minor. Okay, m of 1, 1. Okay, so m11, you delete this row. Okay, row 1, column 1, and then you will find the determinant of this one, the rest column. Okay, so this determinant of this matrix will be 5 multiplied by 8 minus 4 multiplied by 6. Okay, and that will equal to 16. Okay, what about the cofactor of it? So C11 will be minus 1 to the power of 2 multiplied by minor 1, 1. So it's still 16. Okay. Now, try to calculate another one. What would be the minor of 832? So you delete the row number 3 and column number 2. So you want to calculate this one. So this will be 3 multiplied by 6 minus 4 multiplied by 2. Okay, that will be 26. What about the cofactor? The cofactor here, you see here, minus 1 multiplied by 3 plus 2, so minus 1 to the power of 5, so it will be equals to minus m of the minor 32, which is this one, minus 26. Okay, now we use the our understanding about minors as well as cofactors to check the formula of calculating determinants for 2 by 2 matrix A. First of all, to make it easier to calculate uh, to the formula of those minus 1 to the power of I plus j that we have to for calculating the cofactors, we use this checkerboard, because this one, whenever we have the same I and j value, we will have the even number of I plus j, we will have a positive sign, and we have odd number for I plus j, we will have negative sign. So for example, this one is 1 plus 1 is even number, so we have positive. This one 1 plus 2 is a negative, so here we have negative, this one will be positive. Okay, this will be easier for us to calculating a lot of part of the cofactor values. So with that case means that if we have the value of a CII, cofactor of 1 1 will be equals to the minor of M1. The 1 1 value is equal to the same one, which is A22 here. Remember, we have this matrix A will be equals to the contents A11, A12, A21, and A22. Okay, so the cofactor for 1 2 will be equals this. Cofactors of 2 1 will be equals this. 2 2 will be equals this. Now, if you want to calculate the determinants of matrix A, which consists of this value, then the formula will become it will be equals A11 multiplied by cofactors of 1 1 plus A12 equals to cofactor of 1 2. Or if we go back to the previous formula, which is this one, so it will be the same, right? A11 plus multiplied by A22, which is C11 here, and plus A12 multiplied by minus, because it's A21 is minus A21. Okay, so this will be lead, and it's equal for both all of this, and this will be called later on as the approach to calculate a cofactor determinant by so-called cofactor expansion. Okay, this one. Okay, we have seen the formula that being discussed earlier. Now we will create a general definitions for calculating determinants for any n by n matrix. So the theorem is mentioned as follow. So if an A is a n by n matrix, then regardless the row or column of the chosen from A, you can use the number obtained by multiplying the entry in that row or column by its corresponding cofactors and add all the results of the products, and it will always the same, get you the same results. Therefore, you will have this one when you have an n by n matrix. Okay, and then you find a value or a number that obtained by multiplying the entries in any row or any columns of A by its corresponding cofactors and adding the result of the products, you can get the determinants of those values. So it sums up that the value of this process called cofactor expansion of A. Okay, So cofactor expansion along the J column can be a cofactor expansion along the I column. Both will get you to the value of the determinants of those particular matrix. Okay, now let's use the particular definition and theorem from previous one to calculate a 3 by 3 matrix, the determinant of this 3 by 3 matrix A. Okay, now you can choose either which row or which column to conduct the cofactor expansion process. And now for this example, we choose the first row. Okay, for the first row means that you will use this one, this row, cofactor expansion along that row. Okay, sorry, that one is column. Cofactor of expansion of the first row means this one. Okay, so first of all, then you need to do it one by one. So it will be the first one, this one, and then so 3 here. Remember, you still have the checkerboard, so plus minus plus minus plus minus plus minus plus. Okay, so plus 3, then you delete this one, and then you need to find determinants of the rest of the entry that is not deleted. So minus 4, 3 here, this one, minus 4 3 4 minus 2. Okay, that is for the first row. And then for the second row, now we move on that this one. Okay, you will delete this and then this. Okay, so you have minus 2, sorry, second row, not so you will cofactor around the row, so you go to the second column, so it will be this one. Okay, because you have sign minus here, minus 1 multiplied by the one that you delete here is this and this, minus 2 3 5 minus 2. So this you need to find the determinants of it. Okay, next go expand along the row, so you go move to the third column now. So this one you have plus sign, plus 0, and then the rest of the matrix that is left is minus 2 minus 4 5 4. Okay, now it's already become a 2 by 2 matrix, so it is easy to calculate the determinant of this one. Okay, so this will be 3 multiplied by, okay, this one minus 4 multiplied by minus 2, so 8 minus 4 multiplied by 3, so it will be 12 minus, sorry, 8 minus 12, so the rest will be equal this minus 4. Okay, minus this one, minus 1 multiplied by minus 2 multiplied by minus 2 minus 5 multiplied by 3, so you get this one minus 11, plus, since this one is 0 multiplied by something, always 0, so here you can check the calculation. I suppose this will be the result will be minus 1. Okay, so the determinant of this matrix is minus 1. Okay, so in order to, for the sake of showing you that cofactor expansions can be done in any row or any column, so let's try do another example that we do the cofactor expansion along the column, the first column, so along with this one. Okay, so first you have 3, this one, so you delete this, so you have this matrix, same with the previous one. Okay, But the next one, instead of move along the row, you move along the column. So the next one is this one, minus 2. Okay, and then you delete this, multiplied by 1 0 4 minus 2, determinant of this. Okay, and then finally you go to the last row because you move along the first column, this one. So plus 5, plus is from this one, positive sign, 1 0 minus 4 3. See, you see that from example 3 and 4, example 3 is having much less calculations because the last one is multiplied by 0. As a rule, one of the best strategy for cofactor expansion is to expand along row or column with the most 0. Okay, now let's choose to do a more complex calculations. You have a 4 by 4 matrix. Okay, now you want to use a cofactor expansion for that, calculating those determinant of this 4 by 4 matrix. Okay, now in order to do that, first of course you will need to choose the one that has the most 0 from this matrix. So you can choose this one. Okay, remember you still have the checkerboard, plus minus plus minus minus plus minus plus plus minus plus minus minus plus minus plus. Okay, then if you expand from this second column, so it means that you will have 0 multiplied this one, yeah, set, multiplied by some matrix, plus the second one, this one, 1 multiplied by, okay, the 3 by 3 matrix will be this one, 1 multiplied by 1 0 minus 1 1 minus 2 1 2 0 1. Yeah, exactly this one. Yeah. Okay, and then the rest of it is again 0 multiplied by some matrix, plus, sorry, this one plus column second row. Oh yeah, this one minus, this one plus, this one minus, this one plus. But since the one that has value only this, so you will have like this one, the calculation of the expanding the second column. Okay, but this one is not complete yet. You still have this one, right? You need to calculate the determinant. How do you calculate the determinant of that particular matrix? Okay, you can choose again which column you can, it's easier for you to use. So I think this one, because this only have only this have 2 zeros here, so you just need to calculate the third one here. Okay, the expansion of this. Remember, you still need to check the checkerboard, plus minus plus minus plus minus plus minus plus. So the last one is minus plus. Okay, so this one, send this one minus 2 multiplied by the determinant of 1 minus 1 2 1. Okay, so 1 minus 1 2 1. Okay, now this one is easy. This 1 multiplied by 1 minus 2 by minus 1, so 1 plus 2. So there you got the determinant of it. Okay, after understanding the formula on calculating determinants using cofactor expansion approach, now that we can prove on calculating determinant for upper triangular matrix, it will be ends up to the multiplications of the diagonal of those matrix. Okay, based on the cofactor expansion approach, now we can wisely choose that, okay, in order to calculate this, we can choose row or column that has the most zero value. Yeah, that's the wise way to choose cofactor row or column based on the cofactor expansion approach. Let's say we are choosing this one. Okay, this the first row. So the formula will be like, okay, since this all was zero, so the one that we need to expand only this one. So it will be the value will be a11 multiplied by the determinant of the rest of this, right? So it is this one. Okay. Okay. Soon after that means that we need to calculate the next uh, determinants we need to calculate here, and again we will wisely choose all the one that have the most zero in its row or column. In this case we choose this one. So this row means that we only need to expand the value of the first row, since this one both is zero, right? So it will be the previous one, a11 multiplied by a22 multiplied by the determinants for this matrix, which is the minor of the one that we just eliminate. Okay, and then finally we have here, we can choose another row, this one, to calculate this, which is this one. So means that it will be a1 a2 multiplied by a33 and the determinants of a44. And remember, a single entry metric determinant is the entry itself, so it will be a11 a22 a33 a44, which equals to its diagonal. Next, for a spatial matrix with size of 2 by 2 matrix and 3 by 3 matrix, there is a useful techniques that we can use to calculate its determinants. Different with compared to the cofactor expansions, this approach need to have some uh, it is easier to calculate due to its pattern that is quite somewhat easy to follow. For example, for a 2 by 2 matrix, the first that you need to do is to draw a horizontal line. First one is go straight down below like this. The another one is go to the from top right to the bottom left. Okay, that is in the same direction. So in this one, you are forming a product of the entry from the rightward arrow and then subtracting the product of the entry with the leftward arrow. Okay, so means that for this one, you will have like the one that from top left to the right bottom is the first one, a11 multiplied by a22 minus subtract with the one that go to the leftward arrow, so a12 multiplied by a22. Okay, for a 3 by 3 matrix, what you can do is that you need to mirror first the matrix because it has 3 columns. Okay, so the column you need to add a arbitrary column number 4 and number 5, which is equals to the first column and second column. Okay, that one, the pivot points, this is number 4, number 5. You see that this one, number 1 is equal to number 4, number 2 is equal to number 5. Okay, and then you can draw again a line that is rightwards here, this one, okay, and then this one, and then another line is this one, and this one. Okay, and then the same approach in which you need to sum all the rightwards and then subtract all the leftward. So here we will have a11. Okay, let me delete this first. So the first term is that you will have this one, the first term here is equal to this one, which is A11 plus A22 plus A33. Yep. And then this next one plus again, yeah, A12, A23, A31. This one, second one. And then the third one is this one, A13 plus multiplied by A21 multiplied by A32, which is this one. Okay, and then now we go to the downward, left downward, so leftward arrow. So this one is number 4 here, you see, A13, okay, this one, oh yeah, minus number 4, yeah, this one, A13, A22, A31, which is this one. And then number 5 here, yeah, this one, okay, plus, yeah, minus 4 minus 5, 5 is what? A11, A23, A32. Here, where is it? No, sorry, 4, 5, yeah, A11, A23, A32. And this, so this one number 5 here. And then number 3, number 6 here, A21, okay, A12, A21, and then A33, which is this one. I don't know why they like switch the sequence like that, but the calculation is correct. Okay, this the techniques that we learned earlier, we can apply it to calculate this 2 by 2 matrix and 3 by 3 matrix. So take example of this one. So this will be this one minus this one, yeah, 3 multiplied by minus 2 minus 1 multiplied by 4. This one is minus 6 minus 4 minus 10. Yeah, and then this one is take quite longer, so we have 1 2 3. First you need to mirror, right, this one and this one, yeah, and then we have 4 5 6. Okay, so the first one, 1 multiplied by 5 multiplied by 9 is 45. 2 multiplied by 6 multiplied by 7 is 84. 3 multiplied by minus 4 multiplied by minus x, 96. Minus, yeah, 4, yes, this one, the fourth one, 7 multiplied by 5, 35, multiplied by 3, 105. And then the fifth one, yeah, this one, 1 multiplied by 6 multiplied by minus 8, so minus 48. Then the last one, 2 multiplied by minus 4 multiplied by 9, minus 72. Then you calculate all of this, you will get this one as the determinant. Okay, next is that we talk about another theorem where this build-up theorem where it will lead us to show an efficient procedure on evaluating a determinant of a square matrix of any size. The first theorem here is mentioning that if you have a square matrix and there is a row of zeros or columns of 0, so you have a matrix, square matrix, let's say 3 by 3 like this. So either if you have a 0 like this, in any of the position of the row, can be the first row, can be in the second row, yeah. If you have something that's 0 like this, yeah, doesn't have to be 2, can be only 1, then the determinant will be 0 of that particular matrix, let's say matrix A. Also, not only about row, but also column. Let's say this one in the second column. Can be in the second column, can be in the third column. At least you have one column, all is the row of the equals to 0, then the determinant is 0. How does it become like that? Because you remember that in a cofactor expansion, you can choose any row to multiply with its minor. So when you have every value that is multiplied with the cofactor, sorry, not the minor, multiplied by 0, the end product would equal to 0. Okay. Later, it will relate that the determinant of matrix and the determinant of its transpose the corresponding C of those two relationships. Another theorem that also built up to our discussion later on is this theorem where when we have a square matrix A, the determinant of A will be equals to determinants of A transpose. Why? Because transposing a matrix, changing its column to row and its row to column. Almost every theorem about row of a determinant has a companion version about column and vice versa. Therefore, transposing matrix change its column to row and its row to column. The cofactor expansion along any row is the same with the expansion of A transpose along the corresponding column. Yeah, it's just from row to column, because it doesn't matter you expand it to row or column, then the determinant of both A and A transpose will be having the same value. Next is about several perhaps new theorema that you may not found earlier. Okay, let's say we have an n by n matrix. When we have a B is a matrix that is the result of a single row or single column of A is multiplied by a scalar K. Then you will have determinant of B will be equals K multiplied by determinant of A. What does it mean? So let's say you have a matrix B, and then you have the entry here, something, and then you have matrix A here. You have like yeah, A11, A12, A13, and then you have A21, A22, A23, A31, A32, A33, something like this. Okay, and then you have the value of B. Let's say, let's use maybe the third row. So this all the same: A11, A12, A13, A21, A22, A23. So the same, but here we have K multiplied by A31, K multiplied by A32, and then K multiplied by A33. So there is one of the row or multiplications of this one. Okay, so later when you calculate this determinants of A, yeah, this one, to calculate the determinant of B, because this relationship based on this theorem, you don't need to recalculate it again. You just need to calculate, just need to multiply K with the previous determinant of A that you already calculated. Okay, okay, that's about it. And then this one, another one, when you have a B matrix, result of two row or two column of A were interchanged. So the determinant of B will be equals to minus determinant of A. So in this case, B here, so we still have the same A here, okay? So B will be like interchange, let's say the first row and the second row. So A21, A22, A123. A11, A12, A13. The third one, A31, A32, A33. So this will be interchange row. So the original row 1 swaps into the original row 2. So you don't really have to calculate the determinants of matrix B again, because the determinant of matrix B will be equals to minus of determinants of matrix A. So that's how the theorem explain it to you here. Okay. Okay, the last one is that when you have matrix B is the result of multiple of one row of A added to another row of, or when a multiple of one column is added to another column. So the determinant is the same. So it's like when you have B, okay, let's say you add the third row to the first row, okay, so this one will be A1 1 plus A3 1, A1 2 plus A3 2, this one A1 3 plus A3 3, then the rest is the same. So the value of the determinants of this matrix B is equals to determinants of A. Okay, we'll see the formula later on. Okay, here it goes, the things that I just mentioned earlier. So this one is the determinants of matrix B. This is the symbol. So it will be K multiplied by the determinants of original matrix A here. What if the one that you is not from the row in the column here? It's still the same. Determinant of B will be K multiplied by determinant of A. And then this one is when you interchange the row, this one, you see that this first and second row is being interchanged from the original one here. Then the determinant of new one will be equals to determinant or minus determinants of the original one A. And then this one, multiple of the second row of A is added to the first row. So this one, K multiplied by A21 plus K multiplied by A22, K multiplied by A23. The determinants is still the same. Based on this theorem, we will use it to do several elementary row operations so that it is easier to calculate the determinants of a matrix. Okay, now let's talk about determinant of elementary matrix, and then we can use the things that we discussed earlier, the theorema. Let's say if you have this matrix, this is a 4 by 4 matrix, and then we have the original matrix look like this, and then 0 0 1 0 0 0 0 1. Okay, the determinants of this is the diagonals of it, multiplication of it, so it's 1, right? And then you have this matrix B. So actually this one is 3 multiplied by 1, right? 3 multiplied by 0, 3 multiplied by 0, 3 multiplied by 0. So the determinants of this matrix, yeah, you can use the first, the original one is the K, which is 3 multiplied by this matrix A, determinants of A. Yeah, this is to be okay. So it will be 3 multiplied by 1. So it's equal 3. Or you can calculate based on the multiplication of the triangle diagonal as well. But this, since we are implementing the previous theorem, so this is the approach that you are using. Okay, next example is about the second second theorem that we learned earlier. So in this one, you see that they exchange row 4, and then this one is the original row 1. Okay, since this will be this matrix, let's say B, is equals to the will be equals to, yeah, because you change it once, so it is minus determinants of A. Yeah, so it will be determinant of A is 1 minus 1. Okay, the last one is this one, determinants of this. To get this matrix, you can have like a row, the new row 1, yeah, here, this one, the new row 1 will be equals to 7 multiplied by row 4, this one, yeah, plus the original row 1, yeah, so then you will have this one. In that case, yeah, you see that we do the multiplications of a row, yeah, row 4, this one, and then we add it to the first row, and then become the new row 1. So it means that for this case, determinants of this new matrix, let's say B, will be equals to determinants of the original matrix A. So this will be the determinants. So that's how you can use the previous theorem in order to help you to calculate the determinants of elementary matrix. Next is about if you have 0 rows or 0 column. Okay, so but for this one we specifically discuss about 0 rows. When you have when you can calculate a computational that you can introduce a row of 0 because there are two proportional row. For example, this one, the row 1 and the row 2, if you can do like, okay, new row 2 equals to minus 2 row 1 plus row 2. This one will not change the value of the matrix, right? And doesn't change the meanings of the linear system. So with doing this, you will have this one equals 0. Okay, and if you remember, when you have a row equals to 0, the determinant is 0. Okay, again for this one also, this one, how can you make it 0? So the new row 2 equals to 2 multiplied by row 1 plus row 2. So you will have 1 minus 1, 4, 0, 0. Okay, this determinant is 0. For this one, yeah, it will be between which one? I'm not sure. You can help me with this one. Maybe later on. We can check again. This one. Maybe the column. Yep, the column. Okay, this one. It's not always applied to the row for determinants case. Okay. So for example, this one, column 2. The new column 2 equals to column 1 plus 2 multiplied by column 1 plus original column 2. So this one you can have become 1 minus 4 2 0 0 0 7 5 3. Then this will be a 0 column, so the determinant is equal to 0 as well. For this one, what do we have here? I think this and this. Yeah, you can make it one of the row is equal to 0. Okay, next is that we will learn also how to use row reduction using elementary row operations to evaluate a determinant. Okay, because elementary row operations, you remember we have 3. You can do swap, you can do multiplication, you can do uh, row x plus row y, or multiply first something here k with row x plus row y will be equals to new row x, something like that. So these 3 called elementary row operations. So based on this, you can modify this matrix, yeah, because it's come from, yeah, we assume that it's come from a linear equation system. Then you want to solve it, then you want to, let's say first you want to find the determinants of it. So one of the way that we can use is, okay, why don't we reduce the A to its row echelon form, okay, in which it means that we have the diagonals, and then below the diagonals all equal to 0. That is row echelon form. But if it is upper the diagonal also equals 0, it is elementary row echelon form. Okay, so row echelon form is a upper triangular matrix. Okay, and then we can apply the theorem that we learned earlier to calculate the value of the determinant value of this matrix. First, okay, let's memorize a little bit about elementary row operations. First thing first is that we want the leading one is here. In this case, we don't have it yet, so we can interchange this row. Okay, these two rows, the first and the second row are interchanged. So you have new value here. Okay, 3 minus 6, 9, 1, 5, 2, 6, 1. So remember, when you interchange a row, so the determinants of it will be the negative signs of the previous one, right? So when you have a row interchange, introduce a negative sign. And then you have like, okay, this matrix we can have common factor 3, this one from here. And then you take it away, here you put it, okay, this new matrix here is 3 multiplied by 1, 3 multiplied by 2, 3 multiplied by 3 here. So for the determinant of it, yeah, you can put the 3 out of the equation here. Minus is based on the interchange, 3 is based on this one. So you will have leading one here, right? Okay, now you want to make this one 0, right? To make this one 0, how do you do it? So the new row 3 will be equals to this one, row 1, row 2, row 1, row 2, row 3. The is equal to minus 2 multiplied by row 1 plus the original row 3. Okay, so you have 1 multiplied by minus 2, minus 2, minus 2 multiplied by minus 2, 4, minus 2 multiplied by 3, minus 6, plus 2, 6, 1, plus 0, 10, minus 5. So you have this one, 0, 10, minus 5. And remember, multiplication with some row plus another row is not going to change the determinant of it. So no changing here, right? And next, what you have this one already 0 below here. Second one is this one. You want to make this one become 0. So what you did is the new row 3, yeah, equals to minus 10 multiplied by row 2 plus the original row 3. Then you will have this. Okay, 0, 0 minus 55. And remember, these formulations doesn't change the determinants. And finally, now you can have this one, take this one out, minus 55, just make it become 1. So you have a common factor minus 55. It is actually minus 55 multiplied by 0 minus 55 multiplied by 0 minus 55 multiplied by 1 to get the original row. And in this case, because you multiplied it with minus 55 as the k value, so you can take this one out, the minus 55 to here. Okay, and then you have the upper triangular matrix or echelon row form, which basically you just need to calculate this value, multiplicate it, and then the determinant will be 1, right? This one minus 3, minus 55, and 1. So then if you multiply this with this, so you get this one, 165 is the determinants of this matrix. Okay, don't get confused with the elementary row operations only. But here, for calculating determinants, okay, this is not to solve the linear equation system. You can use the column operations also to evaluate the determinants. Remember, previously we used row operations. Now you can use column operations. You can see that from this one, yeah, of course you can use the elementary row operations, but it's going to take a longer journey before you can find the determinants of it. But if you take a look of this column, column 2 and column 4, basically if you have the new column 4 will be equals minus 3 column 1 plus column 4, yeah, means that you will have like minus 3 minus 6 0 minus 21 3 6 0 minus 5. Okay, you plus this one plus 0 0 0 minus 26, so you will have this value. Okay, it turns out with this matrix, this is a special matrix where you have an lower triangular matrix where you can calculate the determinants of lower triangular matrix by calculating its diagonal. So it's easier to calculate its determinant. Okay, the next approach is even more complex because we are going to combine row operations with cofactor expansion. Take example of this matrix. You want to calculate the determinants. It seems like, oh, you can do row operations up until it's lower triangular, or you can use this approach which may look simpler. It looks faster. Okay, take example. Okay, for this one you can do like multiplications to get the new row 1 will be equals to minus 3 row 2 plus row 1. The new row 3 will be equals minus 2 row 2 plus, sorry, row 2, yeah, minus 2 row 2 plus row 3. And then row 4, the new row 4 is minus 3 row 2 plus row 4. So basically you try to make this one 0 0 and this one 0. Okay, and then it turns out you get this one, this value. Okay, this matrix. Now because this doesn't change the determinants, yeah, this operation, then you can do, okay, now we have 0 here. Okay, you can do cofactor expansion, in which let's say you choose column 1. Remember, you still have, if you do cofactor expansion, you need to have the what bracket sign, plus minus minus plus minus plus. So here this one is minus, so minus 1 multiplied by, okay, the cofactor expansion will be this, yeah, minus 1 0 1 1 3 8 3 3 0, yeah. Okay, this one. Now, okay, after the result of the cofactor expansion, okay, now you need to calculate again this matrix. Okay, how can you do this? Okay, you can reduce this one to become 0 again. So the new row 3 will be equals to row 1 plus row 3. So then you have this one, this value. Okay, and then, okay, you can do again cofactor expansion of this one. So remember, you should go back to the sign bracket, plus minus plus, yeah, so this one is positive, so his one is positive, so it's positive of minus 1 is still minus 1, yeah. And then you do cofactor expansion, then you need to calculate this matrix, right? Okay, 2 by 2 matrix is already easy. Is this one multiplied by the minus this, the left diagonal, so it actually minus minus 1, so it's plus 1. And then this one 3 multiplied by 3 is 9, minus 3 multiplied by 9 is 27, so you get minus 18. Okay, now let's talk more about several basic properties of determinants. In this slide, we will talk about several possible relationship between, let's say we have a matrix A, matrix B with n by n which are n by n matrix and scalar value k. Let's explore several relationship that between determinant E, determinant B, determinants of a matrix K multiplied by A, determinants of a matrix A plus matrix B, and determinants of matrix A multiplied by B. Okay, the first one. When you have a matrix A multiplied by a scalar K, so it means that later on you have a matrix that looks like this. So if you have each of the row and column were multiplied by K, right? And you remember that for each of these, you can take out the K value. So since you have 3 row with K, so you have K to the power of 3 multiplied by the determinants of regional matrix. However, for okay, this one is okay, right? When you have determinants of K multiplied by A, you can calculate it simply by K to the power of n multiplied by the determinant of A. However, for the rest of the relationship, like A plus B, there is no particular emphasis that can show a relationship between A plus B. It is just known that determinant A plus B is not always equal to determinant A plus determinant B. Okay, here we can see that the example of how determinant A plus B will not be equals to determinant A plus determinant B. For example, you have here A is equal 1, 2, 2, 5, B is equal 3, 1, 1, 3. A plus B is this one, yeah, 1 plus 3, 2 plus 1, 2 plus 1, 5 plus 3. Get this matrix. And then you know that the determinants of A here is 1. Yeah, 1 multiplied by 5 minus 2 multiplied by 2. 5 minus 4. The determinants of B is 3 multiplied by 3, 9 minus 1, 8. Yeah. And here the determinant is 4 multiplied by 8 minus 24 minus 3 multiplied by 32 minus 9. It's 23. So you see that 1, yeah, determinant A plus B is 23. It's not equals to 1 plus 8. Yeah, no. Okay, in spite of the previous example, this one, there is a useful relationship concerning sum of determinants, which can be applied when it involves the same matrix with the same input except one for one row. Okay, take example. If you have this one A and B, the row is the same, yeah, but this one is different. Okay, then if you have C matrix which will equal to A plus B, how do you calculate C? There is a relationship for that. Okay, first of all, if we expand the calculations of matrix A, matrix B with that particular input, then you will have, okay, this one, A will be this, right, 2 by 2 matrix. B will be this, yeah, another 2 by 2 matrix. Since the corresponding this one 1 1 and 1 2 is the same, so you can have like expanded to this one, yeah. So this one also means what? This one means that it will be equals to determinants of A11, A12, this multiplied by this minus this multiplied by this, right? So if you have a matrix C that is equal to one of the row is equals to summation of matrix A and matrix B, then in order to calculate the new matrix C determinants, you can just plus the two determinants of A and B. Okay, take example of the previous concept that you learned. So here we have matrix C is actually the last row here is equals to A plus B here. So in order to calculate determinants of C, you can calculate it by calculating the determinant of A plus determinants of B. Okay, so another one is that okay, if you have determinants of two matrix multiplied, you can calculate it separately. Okay, this one I will skip the explanation, but basically you can use this when you have B is an n by n matrix and E is an elementary matrix. You know what is elementary matrix. If you want to calculate determinants of A multiplied by B, it can be calculated separately. Next, determinant test for invertibility. So basically, when you calculate, why does it important to calculate the determinants? Because the next theorem provides an important criteria for determining whether a matrix is invertible. It also takes us to a step closer from later we will have another formula. So basically, when you have a square matrix is invertible, it is only if the determinant of it is not equal to 0. Okay, now when you have this metric, right, you can see that okay, this one and this one is proportional, so you can change the matrix become 1 2 3 1 0 1 and 0 0 0, so the determinants of this is equal to 0. Thus you can assume, you can conclude that those matrix A is not invertible. Okay, next theorem is that when you have A and B are square matrix with the same size, the determinant of A multiplied by B can be calculated separately. First calculating determinants of A, then multiplied it again with determinant of B. In this slide, we will learn about something called adjoint matrix. So basically, all the way in this slide, we discuss a lot on calculating determinants because at the end of the day we can use the determinants to calculate the value of variables of linear systems that we want to solve. Okay, in this one we will you will introduce to another matrix called Cij, which consists of matrix of cofactors of A. Okay, so how do you calculate Cij matrix? So basically you need to calculate one by one from each entry the cofactors value of it, and then after you got this cofactor matrix, if you transpose it, it becomes something called the adjoint matrix of A. You can use adjoint matrix of A to calculate the value of x variables that we want to find in the linear system. Okay, here we try to calculate um, the cofactors matrix of this A 3 by 3 matrix. So take example the first one here, the C11 is the value of minus 1 multiplied by 2, so sorry 1 to the power of minus 1 to the power of 2, so you get, and then multiplied by the this one, and the determinants of 6 3 minus 4 0, so you have 1, and then this one 6 multiplied by 0 0 minus 3 divided by minus 4, so you get 12 here. So this one, right? So something like that, and then finally you will calculate each of it: C12, C13, C21, C22, C23, C31, C32, C33. and you will get this. And then you transpose this, row become column, yeah, and then this one become this one, this one become this one. Then you have the adjoint matrix of A. Later you will use this adjoint matrix to calculate the value of the unknown variables in linear system. Okay, so basically those cofactors that we calculate earlier is being used here, cofactor matrix. So if you have this one, so you have this as the linear systems that represented in the matrix form, augmented matrix form. Then if you want to find the x, it's equal to A inverse multiplied by B, and A inverse is 1 divided by the determinant of A multiplied by adjoint of A, right? Adjoint of A is the C cofactor transpose earlier that you have, and then multiplied by B, you will get all of the x value. So basically this is the later on known as Cramer's rules. Basically, you can find for ax equals b n linear equation with n unknown variables with the determinant of e is not equal to 0. You can find the x1 value is equals to determinants of matrix A1, okay, this one, divided by determinants of A. And now the question is, what is A1? A1 is basically the same matrix with A, but instead you replace the J column, let's say 1, the first column, with the right hand side of the A matrix. Okay, so with B here, right hand side, replace this one with B. So this one B1, B2, B3. And you calculate the determinants, you will get the value of X. Okay, let's see how it works. Yeah, this is the formal form of it. Determinant of aj will be this one. Okay, then you will find the xj value is determinant of aj divided by determinant of a. So now let's try to use to solve this one. You have this linear system, 3 equations with 3 unknown variables. Okay. Remember the b value here, the right hand side value is equals to 6, 30, and 8. Okay, and then here is the original A matrix. Yeah, and then this the A1 is replacing this one, the first column, with the B value here. Okay, A2 instead changing the first one, you change the second one. Yeah, A3 you change the third one. Okay, now to find the value of x1, you calculate the determinants of this value divided by determinants of this value. I'll let you choose. You can use any approach to calculate the determinants. We learned a lot earlier. So basically, if you with those approach, you can find that the determinant of A1 is minus 40, determinant of A is 44. Then you will have the value of x1 is minus 10 per 11. And so on and so on. You can calculate x2 and x3. That's how we can use Cramer rules. Therefore, we need to learn how to calculate determinant efficiently so that you can use it easily here. So I think that's all about the materials for these slides. Thank you very much.